Gaseous state. This state is characterized by sensitivity of volume change with change of pressure and temperature. It is due to the large distance between molecules as compared to their own dimensions. There exists weak van der Waals forces. Ideal gas. A gas with no intermolecular attractions and having very negligible volume occupied by molecules when compared with volume of gas is termed as ideal gas. An ideal gas is a hypothetical gas and none of the gases are known as ideal. These gases are called real and they may behave like an ideal gas under specific conditions. Gas laws. Boyle's law. The volume of gas is inversely proportional to the pressure at constant temperature. That is, volume is inversely proportional to pressure. Charles' law. The volume of the gas is directly proportional to the temperature of the gas at constant pressure. V is directly proportional to T. Gay-Lussac's law. The pressure of a gas is directly proportional to the temperature at constant volume. P is directly proportional to T at constant volume. Avogadro's law. The volume of gas increases with increase in number of moles at constant pressure and temperature. V is directly proportional to number of moles at constant pressure and temperature. That is, V1 by V2 is N1 by N2. Dalton's law of partial pressures. P total is PA plus PB and so on, where PA is mole fraction into total pressure. Percentage of gas in the mixture is given by partial pressure by total pressure into 100. Pressure of dry gas is pressure of moist gas minus aqueous tension, where aqueous tension is the pressure of water vapors. Relative humidity of air is given by partial pressure of water in gaseous state by vapor pressure of water in liquid state into 100. Graham's law of diffusion. It states that the rate of diffusion or effusion is inversely proportional to the square root of density. That is, R is inversely proportional to 1 by root T. Ideal gas equation is obtained by combining Boyle's law and Charles' law. That is, PV is equal to nRT, where R is the gas constant. PV is equal to nRT can also be represented in these three forms. Kinetic theory of gases. PV is equal to 1 by 3 mnc square, where c is the root mean square velocity. For 1 gram mole of gas, n is Avogadro number of molecules, m into Na is m. So the equation can be written as PV is equal to 1 by 3 mc square. Kinetic energy per mole is given by 3 by 2 RT. Since n is 1, it can also be written as 3 by 2 PV. Kinetic energy per molecule is given by 3 by 2 RT by Na. It is written as 3 by 2 kT, where k is Boltzmann constant, that is 1.38 into 10 power minus 23 joule per Kelvin per molecule. Here we can also study about Avogadro's law, that is, at constant temperature and pressure, the volume of mixture of gases is equal to the sum of partial volumes of the constituent gases. Types of molecular velocities. RMS velocity, that is root 3 RT by m. It can also be written in these two forms. Average velocity is root 8 RT by pi m. Most probable velocity is root 2 RT by m. The ratio of most probable to average to RMS velocity is given by 1 is to 1.128 is to 1.224. RMS velocity is greater than average velocity is greater than most probable velocity. Maxwell's distribution of curves for velocities. Real gases. Gases which don't obey perfect gas laws over a wide range of pressure and temperature are non-ideal or real gases. The repulsive forces between molecules assist their expansion and attractive forces assist compression. These deviations are due to the interaction of molecules with each other and the volume occupied by gas molecules. Deviation from ideal behavior is due to the curve for real gas has a tendency to coincide with that of an ideal gas at low pressure when the volume is large. At high pressures, however, deviations are observed. Van der Waals equation of state. It is given by P plus A n square by V square into V minus NB is equal to nRT. If the value of A is greater, the gas is easily liquefiable. If the value of B is greater, then the molecule has a larger size. Van der Waals gas equation for real gas comes into picture because the following assumptions of kinetic theory of gases are not followed by the real gases. The volume of gas molecules is negligible in comparison to the volume occupied by the whole gas, which is practically not correct at all pressures. This leads to volume correction. There are no intermolecular forces of attraction, which is practically not observed in real gases. This leads to pressure correction. Where volume correction, V actual is V minus NB, where B is effective volume per molecule, that is 4 by 3 pi r cube into 4. Pressure correction, P actual is P plus P dash, where P dash is given by A n square by V square. At very low pressure and high temperature, P dash and NB can be neglected. That is, we write it as PV is equal to nRT. At low pressure, NB can be neglected. So P plus A by V square into V is equal to RT. That is, Z can be written as 1 minus A by RTV. At high pressure, P dash can be ignored. That is, P into V minus B is given by RT. So Z will be equal to 1 plus PB by RT. At low pressure, Z is less than 1. At high pressure, Z is greater than 1. Here Z is volume occupied by real gas by volume occupied by ideal gas. But in case of hydrogen and helium, due to their small size, we always ignore the internal pressure, that is P dash. So they always show Z greater than 1 at moderate and high pressures. Boyle temperature, the temperature at which real gas obeys Boyle's law in low pressure range. TB is given by A by Br. Inversion temperature, the temperature at which a real gas shows no Joule-Thomson effect. That is, T inversion is given by 2 TB. That is 2A by Br. Critical parameters. Critical temperature, TC. The temperature above which a gas can't be liquefied by applying any extent of pressure. TC is 8A by 27 RB. Critical pressure, the pressure required to apply on a gas to liquefy at a critical temperature, that is A by 27 B square. Critical volume, the volume attained by a gas at critical temperature and pressure, that is V is equal to 3B. The law of corresponding states can also be given by pressure of real gas is equal to P by pressure at critical temperature. Temperature of real gas can be given by T by temperature at critical temperature. Volume of real gas can be given by V by volume at critical temperature. This is an important equation, please remember it. When we substitute the values of PC, VC and TC, we get Z as 3 by 8. That is compressibility factor at critical temperature, pressure and volume. Thank you.